Okay, we have here today a really interesting integral on the board. This is from MIT Integration Bee 2014, problem 4. We have the integral from 0 to 2 of this infinitely nested square root dx. Okay, this is actually an integral that I did not too long ago, just a week or so back. There were some interesting suggestions in the comments of using an alternative method, and I wanted to explore that in this video. So to get started with this, the first step is going to be similar, or actually the exact same thing as the previous video, where I just set this whole nested square root equal to y. So let's just write that out. And then what I'll do first is just square both sides. So we'll have y squared equals x squared plus this nested radical again. But the thing to notice now is this thing here, this is actually just, again, the same nested radical. This is going to be y again. So I can write my y squared as equal to x plus y. And then just rearrange it and get the y's on one side and the x's on one side. So we can write this as y squared minus y equals x. And now this is where it differs. In my first video, what I did is I went and solved for y. But in the alternative method, what we're going to do is take a derivative to find our dx right here. So we'll take the derivative on the left side and we get 2y minus 1 dy. And derivative of x is just going to be 1 dx. So this is going to allow us to make a substitution because now we have a way to write our dx in terms of y. And we have this whole nested radical in terms of y. Now we could go ahead and make the substitution, but we're going to need to update the bounds. Now we could kind of do it informally using this equation. It's not too hard to find some values in order to update our bounds, but we want to be careful here because the bounds are actually kind of tricky. So I'm actually gonna do what I did in the previous video, and I'm gonna turn this into a quadratic, just subtracting an x on both sides. And then we'll use the quadratic formula on this. So like our b value is minus 1, so minus b gives me a 1, plus or minus square root of b squared is just 1, minus 4, a is going to be just 1, and then c is going to be this minus x, and this is all going to be over 2a, or just 2. And then I can just simplify this. I'll divide the half in, so we'll have 1/2 plus or minus 1/2. Then simplifying what's in the radical, we get 1 plus 4x. And then we just need to deal with this plus or minus. Now let's just notice that y is always going to be positive or 0. Now technically y could be 0 when x is 0, but because this is an integral, we're not interested in what happens exactly at 0. So excluding that, this thing is always positive. If you look at a graph of this, when this is a minus, well then this whole thing is going to always be negative, or except for at that one point at 0. So we can just eliminate this negative part because it's never going to be true. So then we'll go ahead and make the substitution, but we'll use this value right here in order to update our bounds. So now we'll go ahead with this, and first what we'll do is we'll take a 2 here. So let's just see what happens. If we say x is equal to 2, this is going to become, for our y value, this is going to be 1/2 plus 1/2. Then putting a 2 in here, we get 8 plus 1, or 9. But then simplifying square root of 9 is just 3, so we have 3/2 plus 1/2, or just 2. So therefore our upper bound is going to be 2. Next we'll evaluate this at 0, so we're saying x equals 0. So for our y value, we have 1/2 plus 1/2. Plugging 0 in here, this just gives me square root of 1. So we end up with 1/2 plus 1/2. So our lower bound is going to be 1. And again, this is where a lot of the problems occur, because it's easy to think that when x is 0, this whole thing is 0. Well, yes, when x is exactly 0, this is 0. But you really have to think of this, you have to kind of think of this as like 0 plus. If you were to look at this with a calculator, or you look at the graph, even if you put in a really small number like 0.001, this thing blows up to 1 like almost immediately. Now again, this whole radical is going to be y, and we'll use our dx value from over here, which is 2y minus 1 dy. We'll just distribute in this y, so we're integrating from 1 to 2. We're going to have 2y squared minus y dy. We can just integrate this with power rule, and we're going to have 2/3 y cubed minus y squared over 2, evaluated from 1 to 2. So let's just go ahead and evaluate this thing. So 2 cubed is 8, so we'll have 16 over 3 here, minus 2 squared, we're going to have minus 4 over 2 here. Then plugging in 1, this is just going to give me 2/3 minus 1/2. And I think what I'll do on this is just get a common denominator of 6 for everything. So I can write this as 32 over 6 minus 12 over 6. Distributing the minus here, we're going to have minus 4 over 6. Minus times minus is plus 3 over 6. Adding all this up, we get our final solution of just 19 over 6. Okay, really interesting method. I think the trickiest part of this problem was really the bounds. So we'll stop it there. Thanks everyone for watching. Have a good day.